Hey, welcome back. In this video, we're going to discuss closures of relations. In the last video, we started to discuss relations. We defined a relation from a set X to a set Y just as a subset of the Cartesian product of X with Y. We also defined a relation on a set X just as a relation from X to X. In the same video, we defined several properties of relations. We said that a relation R on the set big X is reflexive if and only if for all elements little x in big X, we have the ordered pair little x in our relation R. And we saw several examples of relations that are reflexive. For example, the equality relation. And the equality relation, specifically, I'm talking about this relation. And we're assuming that this is a relation on some set X. So little x is an element of our set X, and little y is an element of our set X. So that's what I mean when I say the equality relation. And similarly, we can define the less than or equal to relation, which is also reflexive because we have x is less than or equal to x, just like we have x equals x. And we can also define a subset relation where our elements, instead of being real numbers or integers, they are sets. And that is also reflexive. Another one we saw in the last video is the equivalence mod m relation. That one's reflexive. And the divides relation. The divides relation, the ordered pairs x, y for which x divides y. Another property of relations that we discussed in the last video is symmetry. And we say that a relation R on the set big X is symmetric if and only if for all little x in big X and for all little y in big X, we have the ordered pair xy in our relation if and only if the ordered pair yx is in our relation. Some examples of relations that we saw in the last video, which are symmetric, are the equality relation, so the one at the top here, and the equivalence mod m relation. And both of these were also reflexive. And an example of a relation that is symmetric but not reflexive would be, for example, the inequality relation. So that one is symmetric because if x does not equal y, then y does not equal x. But it's not reflexive because it's not true that x does not equal x, because we know that x must equal x. So that's an example that is symmetric but not reflexive. And the other two were both symmetric and reflexive. So the third property that we discussed in the last video was anti-symmetry. And it's not exactly the opposite of symmetry because there are relations which satisfy both symmetry and anti-symmetry, specifically the equality relation we saw. The property of anti-symmetry says for all little x in big X and for all little y in big X, if we have both ordered pairs xy and yx in our relation, then we must have x equal to y. And we saw some relations in the last video which were anti-symmetric. For example, the equality relation, like I mentioned before, the less than or equal to relation, because if we have x less than or equal to y and y less than or equal to x, then we must have x equals y. Also the subset relation. So with sets, if we have set S a subset of set T and T a subset of S, then we must have S equals T. And the divides relation as well. If x divides y and y divides x, then we know that x is less than or equal to y and y is less than or equal to x. So we get x equals y again. And the last property we discussed is the longest definition of all. It has three quantifiers. It says for all little x in big X, for all little y in big X, for all little z in big X, if we have both ordered pairs xy and yz in our relation, then we have the ordered pair xz in our relation. And some relations we saw which are transitive were equality, less than or equal to, subset, equivalence mod m, divides, and less than. In this video, we're going to discuss a new topic related to the properties that we saw on the last slide. And this topic is closures of relations. Specifically, we will discuss what is called the P closure of a relation R, where P is some property of relations. Here is the specific definition of the P closure, and we will use this definition to find the reflexive closure, the symmetric closure, and the transitive closure. Let P be any property of relations. Let R be any relation, which could have property P, or maybe it doesn't. If there exists a relation R prime with the property that R prime has property P, R is a subset of R prime, and R prime is a subset of L for any relation L that contains R and has property P. If these three requirements are satisfied for the relation R prime, then we call R prime the P closure of R. And we're going to focus in this video how to find the P closure for three properties P, which we discussed in the last video. The first is the property of being reflexive. Next, we will discuss how to find the symmetric closure, and then we will go over the transitive closure. And this is an approximate order of difficulty of computing each of these closures. So reflexive closure, I think, is the simplest one. To calculate the reflexive closure of some relation R on a set big X, we just calculate this new relation R prime, which is equal to R union the set of ordered pairs little x comma little x for little x in the set big X. This set on the right is sometimes called the diagonal of the set big X. And we're going to see some examples of how to calculate the reflexive closure of some relation on some set. We're going to use a small set here, the set X equals 1, 2, 3, 4. There's our first relation on the set big X, and here is its reflexive closure. In order to find the reflexive closure, I'm just going to take the union of R right there with the set of those ordered pairs on the diagonal of my set big X. My diagonal consists of 1, 1, 2, 2, 3, 3, and 4, 4. And when I calculate that union, I get the following set. So the set I end up getting has cardinality of 7. And we can see in that case that R and the diagonal had no overlap. R had cardinality 3, the diagonal had cardinality 4, and the reflexive closure had cardinality 7. Let's look at a second example. In this case, R and the diagonal do have an intersection. They intersect at this element, 1, 1. So our reflexive closure, when we calculate R union the diagonal, we get this set. We have R, which is 1, 1, 1, 2, 3, 4. And we also have the elements of the diagonal. We already have 1, 1 in there. So we have to add 2, 2, 3, 3, and 4, 4. So this time, the reflexive closure has cardinality 6 because R had an intersection with the diagonal. Next, we're going to discuss how to calculate the symmetric closure of a relation. In order to find the symmetric closure, we can find another union. This time we take the union of R with its inverse. And the inverse is just the set of ordered pairs yx for which xy is an element of R. So we'll look at some examples now of getting both the inverse and the symmetric closure. And we'll use the same set big X equals 1, 2, 3, 4. So here, with this R, we first find our inverse. R inverse is equal to the following set. We just take each ordered pair and we swap the order of the elements. 2, 1, 3, 2, and 4, 3. And then to find the symmetric closure, we just take R prime equal to R union R inverse, and we find that union. To find the union, we just take the elements of R, 1, 2, 2, 3, and 3, 4. And then we also add on the elements of R inverse, 2, 1, 3, 2, and 4, 3. And that is the symmetric closure of the relation R. Let's look at Another example. So if this is our relation R, then R inverse, we can find that just by swapping the order of each ordered pair. Swapping 1, 1 gives us the same ordered pair, 1, 1. Swapping 1, 2 gives us 2, 1. And swapping 3, 4 gives us 4, 3. So in this case, when we find the symmetric closure, we get R union R inverse. And this gives us 1, 1, 1, 2, 3, 4. And then we add the elements of R inverse, but we already have the 1, 1 in there. So we only need to add the 2, 1 and the 4, 3. And that's our symmetric closure for the second example. Here's one last example. Let's say our set, instead of being 1, 2, 3, 4, our set is the integers. And we'll have R be the less than relation on the integers. So specifically, R here is the following set, consists of ordered pairs, X and Y, for which X is less than Y. So this is the less than relation. And both X and Y are integers. If we want to find the inverse of R, we can just do it the same as we did the ones above. We just take R and we swap the order in the ordered pairs. So we can write it like this, Yx, for which X is less than Y still. And X and Y are both integers. Now, another way we can write that, which means the exact same thing, is as R inverse is equal to the set of ordered pairs Yx for which Y is greater than X. And both X and Y are in the integers. So notice all I did there is instead of writing X less than Y, I wrote Y greater than X. And finally, my last step here for R inverse is to rename my variables. So instead of having the variables X and Y, I'm going to rename the X's as Y's, and I'm going to rename the Y's as X's. So my ordered pairs, instead of being Y's and X, it's going to be an X followed by a Y. And instead of Y greater than X, I have here X greater than Y. And X and Y integers, this part doesn't change. They're both still integers. So all I did there is I took the set right over here and I renamed the X's as Y's and I renamed the Y's as X's. So now I have R inverse in a useful form. And this means I can find my symmetric closure R prime which is equal to R union R inverse. And I can write that as the set of ordered pairs xy, which either satisfy the requirement to be an R, which is that x is less than y and x and y are integers, and the other possible way to be in the union of R union R inverse is if you satisfy the requirement to be an R inverse, which is x greater than y and x and y are integers. So in either case, x and y have to be integers. So we have and x and y are both integers. But we can have x less than y, or we can have x greater than y. So that is our symmetric closure. It's a set of ordered pairs x, y, for which x is less than y, or x is greater than y, and both of them are integers. A simpler way that we can write that is as so. We can write this as a set of ordered pairs x, y, for which x does not equal y, and x and y are both integers. So we saw here that the symmetric closure of the less than relation is the unequal relation. The last type of closure that we will look at in this video is transitive closure. This one usually requires the most calculations to determine. For small sets, sometimes it can be pretty easy to calculate this, but for larger sets, it's usually much more complicated than the two that we already discussed. In order to describe a general, what you could call an algorithm or a method to find the closure, in order to do that, we're going to discuss a couple terms. The first term we'll look at is composition. Suppose that we have two relations on the same set, big X. We'll call them R and S. We're going to define the composition of these relations. We say S composed with R, and we define this as the relation which consists of the ordered pairs x comma z, for which there exists some y, which is an element of the set big X, for which xy is an element of the relation R, and yz is an element of the relation S. And this is the composition S composed with R. And we'll look at how to calculate this with a couple of examples. So here's the first example, and we'll see how to find S composed with R. To find this composition, we can look at each element of R, and we can look at the second term in the ordered pair. And we can see, is there anything in the relation S which starts with that second term. We see something starts with 2 over here. And we take the second term of that pair, what it ends with, because we know it starts with a 2, but we look at what does it end with? It ends with 3. So we take that 1, 3 as the first element of this new relation, the composition. The 1 from here and the 3 from right here. Now I'm going to change the color. And we'll look at this second element of the relation R. And specifically, we'll focus on the second term in the ordered pair, which is a 3. We'll see in our relation S, does anything start with 3? And we see this ordered pair does start with 3. And we look at the second term in that ordered pair, which is the 4. And we take the 2 from here and the 4 from here. We can also check the last ordered pair, the 3, 4. We circle the 4. And we see that nothing over here starts with the 4. So we can't make any more elements of the composition. So over here, we do have something which ends with the 4, but we need something which starts with the 4 to go with this 4. When we're doing the composition, we take the second terms of this relation with the first terms of this relation. So that's our composition, S composed with R. And since S and R are the same here, that's also the composition, R composed with S. Let's look at another example. Here is a longer R. So first we'll do S composed with R. So to find the terms of this relation, we take each ordered pair in R and we look at its second term and we see if we can match that second term with the first term from S. And we see right here we can. So we get 1, 3. We'll do the same with this one. Second term's a 3. We find a 3 here. So we get a 2, 4 there. And then 3, 4, its second term is 4. And there's nothing that starts with a 4 down here in S. 4, 5, its second term is 5. Nothing starts with a 5 in S. Similarly with the 5, 6, and 6, 7. So S composed with R, this is what we get. Now we can look at R composed with S. When we do R composed with S, we start, instead of with the R, we start with the S. So you might be thinking the order that we write this looks kind of funny. You might be thinking we should be writing this one up here as R and then S. Like the order looks weird. But the way we're doing this here is the same order that we compose functions. So when we write F composed with G, the function G is on the inside. The function G is applied to the input first, and then we plug that into F. And so that's why we write the relation composition in an analogous way. So when we compose the composition R composed with S here, we do the ordered pairs of S first. So we have 1, 2. We look at its second term, the 2. We try to match that with the 2 in R, and we find it. The 2 has to be the first term in R, though. So that 2, this one does not work. And that 2 ends with the 3 as the second term. So we can take the 1 here the 3 here to give us a 1, 3. I'll change the color again. Now we'll go on to this ordered pair, the 2, 3. I'll circle that 3, the second term of it. I have to look for that 3 as a first term in R. Here it is. There's the 3. And then I take the 2, the first term, with that 3 as the second term in S, and I put that 2 with the 4, which is the second term when the 3 was the first term in R. So I get 2, 4 right here. And then, let's see, on to the next one, 3, 4. We'll take its second term, the 4. We need to look for something in R that begins with 4. Only this one. And that ends with 5. So we take the 3 and the 5 together. And then we look, and that's the rest of S. So we finish S, and that means our composition is finished. So now that we saw some examples of how to find the composition of some relations, we will see one more term before we see a pretty simple method for calculating the transitive closure. So our last definition before we get to the actual transitive closure is the definition of the powers of a relation. If we have some relation R on the set X, we can define R squared just using composition. We define it as R composed with R. So we actually saw an R squared on the last slide when we had both R and S as the same relation. We can generalize this definition to any power of R. We can define R to the n plus 1 as R to the n composed with R. And with these powers of relations, this gives us a real simple way to find the transitive closure of any relation. We just find the union of all of the powers. And as we'll see, the powers get small very fast. So here, we'll start with a small r. And we'll calculate its transitive closure. So that's r. That's r to the 1. Let's find r squared. So r squared is r composed with r. So I'll write the ordered pairs out so we can, well, I guess we did that on the last slide, so I don't need to write that out. I'll write it out for the next calculation. So we found this one on the last slide. This one was 1, 3 and 2, 4. So now we know r squared. So we'll calculate one that we haven't done yet, the r cubed. R cubed is r squared composed with r. So I'm going to write r right here. 1, 2, 2, 3, 3, 4. I'm going to write the r squared right here. 1, 3, 2, 4. And then we will calculate the composition here. So the composition of these two, r squared composed with r, we take each element of r, we look at its second term, and we try to find a first term in r squared which matches that. So the 2 we need a 2, so 2 is the first term right there. We take the 1 from here, the 4 from here. That gives us a 1, 4. Okay, now we'll go on to a different color. The 2, 3 right here. So this 2, 3, there is a 3 as a second term, and nothing in the r squared begins with 3. So can't make anything with the 2, 3. Similarly with the 3, 4. The 3, 4, its second term is a 4, and nothing in the r squared begins with 4. So all we get here is the 1, 4. So r squared consisted of 1, 3, and 2, 4. R cubed consisted of 1, 4. And let's see what the next one is, r to the 4th. So r to the 4th equals r cubed composed with r. So we can do the calculation right up here. I can just get rid of this and replace it with the 1, 4. And we can see each of these ordered pairs. Their second terms are 2, 3, and 4. And this one over here starts with 1. So we can't put the 2, 3, and 4 matching with the first term of anything over here, because the only thing over there is 1, 4. And 1 is not equal to 2, 3, or 4. So this one is just going to be the empty set. And once you have the empty set, it's going to be the empty set the rest of the way. So the union, it's actually just a finite union. But we write the infinity there because past a certain point, it's all empty sets. So our transitive closure for this one, r prime, is just equal to r union r squared union r cubed, because r to the 4th is the empty set. And that gives us the following set. We have 1, 2, 2, 3, 3, 4. And then we also had the 1, 3, 2, 4 from r squared. And then we have that 1, 4 from r cubed. And that is it. So our transitive closure has 6 elements. Let's look at another one. So here's a larger r. So maybe I'll do its transitive closure up at the top. So for that r, the r squared is going to be r composed with r. And I will write that so we can look at the ordered pairs. So we have 1, 2, so 1, 2, 2, 3, 3, 4, and then we have 5, 6, 6, 7. Okay. And now I will find the composition. So I'll take each of the ordered pairs here. I'll look at their second terms. I have a 2 there. I need to find a 2 over here as the first term, and it only happens with this one. So there's a 2, and its second term's a 3, so I get a 1 and a 3 together. My Second order pair over here is a 2, 3. Second term's a 3. So over here, I need to find something that starts with a 3. 3, 4. So I can take the 2 and the 4 together. Then I have a 3, 4 here. Second term in there is a 4. So I need something that starts with a 4 over here, but there's nothing that starts with a 4. So I can't use that to make anything. Here I have a 5, 6. Second term's a 6. I need something that starts with a 6. I have that right here. So we have the 5 here, and then the 7 from there. And then with the 6, 7, it ends with the 7. There's nothing that starts with the 7 over here. So we can't make anything with that 6, 7. So R squared has 3 elements, the 1, 3, the 2, 4, and the 5, 7. Now we can find R cubed. This is equal to R squared composed with R and to find that, I'll take the R down here. I'll erase the drawings I made on it. And I will erase this right here. And then I will put the R squared here. So R squared right here. So we can do the same process. We take each ordered pair of R, we look at its second term, and try to match it up with the first term in R squared now. And we see the 2 as the second term in R matches up with the 2 as the first term in R squared, giving us the 1 and the 4 together. We look at this 2, 3 right here, and its second term is a 3. Nothing in R squared starts with a 3, so this 2, 3 won't contribute anything. Same with this 3, 4. Its second term is a 4. Nothing in R squared starts with 4, so the 3, 4 contributes nothing. 5, 6 right here. Second term is a 6. Nothing in R squared starts with 6, so that 5, 6 contributes nothing. 6, 7 right here. Second term is a 7. Nothing in R squared over here starts with 7, so the 6, 7 contributes nothing. So for R cubed, our only term was the 1, 4. And finally, we'll calculate R to the 4th. This is R cubed composed with R. And we can calculate that right here, the same as we've been doing the other ones. So here is R cubed, the 1, 4. And we can take each of these ordered pairs and we can look at their second terms, the 2, 3, 4, 6, and 7. And we need that to be the first term of something in R cubed if we want to get any elements. The first term in R cubed is 1. 1's not equal to any of these numbers, 2, 3, 4, 6, or 7. So when we calculate R to the 4th, we just get the empty set. So if we want the transitive closure for this one, we take the union of R, R squared, and R cubed. And together, that gives us the following set. So that is the transitive closure for our second example here, this R. So I'll put an arrow to that one, and I'll put an arrow for this one, which we already calculated was this over here. So we did both of these. And we saw that first transitive closure for 1, 2, 2, 3, 3, 4, it had cardinality 6. And the second transitive closure for 1, 2, 2, 3, 3, 4, and then 5, 6, 6, 7, this one had cardinality 9. So we had a total of 9 ordered pairs here. 5 ordered pairs from R, 3 ordered pairs from R squared, and only 1 ordered pair from R cubed. Let's look at one more relation. Here, let's consider the relation on the set of integers, and it consists of integers x and y, for which y is equal to x plus 1. This R right here is called the successor relation. So here we want to find the transitive closure of the successor relation. So if we want to find the transitive closure, we can get an idea of the terms in R by writing some of them out. So I'll put a dot, dot, dot because R is infinite. But then I'll write some terms here. So we have -4, -3. We have -3, -2. We have -2, -1. We have -1, 0. We have 0 and 1. We have 1 and 2. We have 2 and 3, and so on. So we have all of these ordered pairs, x comma y, for which y equals x plus 1, and they're both integers. So we can order them like this, and that will give us all of them. Now, if we want to find R composed with R to give us R squared, let's take another copy of R below there. So I'll just write the same thing. And we're going to use the same process that we used for those first two relations to find the powers and then the transitive closure. But this time, our powers are not going to become empty. So they're going to continue to have infinite cardinality. But we will quickly see a pattern. So when we calculate the composition of R with itself, I'll put a dot, 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 and we can look at each of these ordered pairs. We have -4, -3 there. We circle its second term. We need to find that second term as the first term in this copy of R down here. And it's only in this one, the -3, -2, to circle it. So we match that -4 and the -2. I'll do the same thing with this -3, -2 here. Its second term is a -2. I need to match that as the first term down here. So -2 there. I'll take this -3 with this -1. Same with this one. -2 and -1. I'll take the -1 as the second term. I need to match that as the first term down here, -1. And that gives me a -2 and a 0. Now this ordered pair, the -1 and 0, its second term is the 0. I need that as the first term down here, and that's only this ordered pair, the 0, 1. So that gives me a -1 and a 1. And I can continue like this, and I get 0 from here with the 2 down here. I also get a 1 with a 3 down here. And it keeps on going. I get a 2, 4, and so on. I can do the same thing to get r cubed. Before we find r cubed, though, we can observe that r squared, the r squared that we just found, we can see that there's a nice way we can write that. All those ordered pairs we found have the same property. We can write them as the set of ordered pairs xy for which both x and y are integers and y is equal to, and we see in all of these examples, all the ordered pairs, y is equal to x plus 2. So our original relation, r, had to satisfy y equals x plus 1. And now r squared, we saw it satisfies y equals x plus 2. Now let's look at r cubed. So r cubed, to find that, we need to do the composition of r squared with r. And we have r squared down here, and we have r up here. So we will work with one of these r's up here, and we'll compose it with the r squared there. So I will erase some of my text on this r. And that should be pretty good. Okay, so now we can calculate the composition of r squared with r. So we have r up here. We'll take its first ordered pair. The -3 is the second term of that. And we need to match that as the first term in r squared. And the only place in r squared where -3 occurs as the first term is right here. And so we can take the -4 from here with the -1 from there. So we have dot, 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 because again, this is infinite. So -4 minus 1. Then we go on to this ordered pair. Its second term is -2. We need -2 as the first term in r squared. That only happens right here. So we can take that -3 with the 0. Here is -2 minus 1. -1 is the second term. We need that as the first term down here. So we can match -2 and 1 here. -1 and 0 right here, the second term 0. We need 0 as the first term down here. There it is. So we get -1 with 2. And we can continue this way. So we have 0, the 1, the 1, 0, and 3. And you might see a pattern now. All of these are 3 apart, and we get 1, 4 next, and then 2, 5, and so on. So we can see there that r cubed also can be described in a really nice way as a set of ordered pairs xy for which both are integers and y is equal to x plus 3. And we can continue this process if you want inductively, or you can just observe that the pattern is going to continue. But if you want to be very careful about it, induction is a good way to go. And you can see that r to the k is equal to, and even without checking it, if we see the first two, 2 and 3, and we look at r to the 1 here, and we see the definitions in each of these, it gives us a good idea of what the definition should be for r to the k. So r to the 1, we had y equals x plus 1. R squared, we had y equals x plus 2. R cubed, we had y equals x plus 3. And so r to the k, we're going to have y is equal to x plus k. And both x and y are integers. And if we want to find the transitive closure of this relation, this last one, this r, the successor relation on the integers, we can just calculate r prime, which is this infinite union, I equals 1. And instead of calling it I, let's call it n equals 1 to infinity of r to the n. And so that's going to be this union n equals 1 to infinity of these sets. And I should have written ordered pair here. So I failed to write that ordered pair. So these sets are all ordered pairs, x comma y. And we can write y equals x plus n. And both x and y are integers. So that is the transitive closure of the successor relation in the integers. And there's a slightly simpler way we can write that, because we can see these ordered pairs here. What ordered pairs do we get? So both x and y have to be integers, and y can equal x plus 1, or y can equal x plus 2, or y can equal x plus 3, or y can equal x plus 4, and so on. So y can be equal to x plus any positive integer. So if we know that x and y are integers, and x can, let me say that again. If we know that x and y are integers, and y can equal x plus any positive integer, then another way to say that is that x and y are integers, and x is less than y. So we can write this in a much simpler way. Instead of as an infinite union, we can write this as the set of ordered pairs, x comma y, for which x and y are both integers, and x is less than y. And that is the transitive closure for the last one. So there it is. So if you take the successor relation on the integers and you find its transitive closure, it will give you the less than relation. So less than, and not equal, but less than. So just the strict less than. And I think that is our last example. So thanks for watching.